Good morning, everyone. It's really good to be able to talk to you today about the CARE UCR project findings. Just as Anya said, I really appreciate that you don't share what's being said today. We don't want anything to compromise that publication. I'm very excited about this project. I have been since we first started, and I'm going to give you some more detail about what was actually done, some more details on the background, and very much state of the art where we are now. Now, many of you, those of you that know me, know that I like to start a presentation or a webinar with a question. Now, I'm not expecting you to answer this, but I want you to give some thought to this, at least over the first few slides that I'm going to give to you, because it's really quite important. And the question is this: if the internal combustion engine has got cleaner and exhaust pipe emissions have reduced, why is urban air quality declining? I'm not going to expect an answer from you on that, but keep that in your mind, and I'll give you some idea of where we may be going with this. And I'm going to ask you to consider non-exhaust emission species, things like paints, cosmetics, consumer goods, a whole range of materials that have been become known as volatile consumer products. They have been found to have quite a significant influence on air quality, and that kind of steers you in a particular direction, or may steer you into a particular direction, and ask, well, what about the asphalt? What about the bitumen? What about the materials that vehicles use to get from point A to point B? And it's with that background that you start to understand why, since 2020, there has been such a big focus on the asphalt itself and the potential contribution that asphalt can make to urban air quality. The first real significant paper that was published was in 2020 by Piyush Khare, working out of the University of Yale in the USA. And the title for that was "Asphalt-Related Emissions Are a Major Missing Non-Traditional Source of Secondary Organic Aerosols, Precursors." I won't go through the paper in detail, but let me just give you a figure. And again, I would like you to hold this figure in your head as we go through. So the Yale paper said that an asphalt pavement could be expected to lose 0.1% of its total mass as volatile organic carbon, and that volatile organic carbon would make its way into the atmosphere and cause potentially secondary organic aerosol. Interestingly, when you look at that paper, what it said was it didn't matter where the bitumen was within the pavement, that the emission pathway, the way that the volatile organic carbon could get out of the pavement, was unaffected by its location. Now, that's quite a big statement to make. So hold those comments as we go through. The second one that causes real concern was a paper by David Humes and his team, working out of Carnegie Mellon University, again in the USA. And they said that emissions from asphalt pavement in service could constitute around about 0.6 micrograms per cubic meter. And if you calculate that over the length of the pavement lifetime, and here we assume around about 20 years, that the emissions generated in service far exceeded those from pavement construction. Again, quite a big statement. Further papers have been published by Seltzer et al. Now, David Seltzer, is the director of the US Environmental Protection Agency. That 2023 paper was effectively a rewrite of the 2020 paper by CARE et al. But it caused concern because for the first time, really, you had someone from a regulatory body authoring a paper or co-authoring a paper saying that there was potential for asphalt to cause significant deterioration in urban air quality and significant concentration of secondary organic aerosol. So it was going to be a problem. And the original author, he hasn't gone away. He's now based at the Scherer Institute in Switzerland, and is continuing to publish these papers. And there's other interest elsewhere. Over the period 2020 to where we are now, there have been papers published in France, specifically out of the University of Lille, in China, in Australia. So you can see that there's this clear focus now on emissions from asphalt and their contribution to urban air quality and pollution. Okay, so that's the background. I'm going to need to give you some definitions because I may lapse into jargon. Apologies for doing that if I do that too often, but here's some definitions. We talk about secondary organic aerosol. Those are pollutants which are formed by the oxidation of volatile organic carbons. That leads us to VOCs. These are organic compounds primarily that have a high volatility at ambient temperature. That's important. That's important because they make their way into the atmosphere and then they can react to form our secondary organic aerosol. Underneath those, there are two other classes of materials that also contribute to urban air pollution. The semi-volatile organic carbons, or SVOCs, with low volatility, but they can make their way into the atmosphere, typically boiling point 240 to 400 C, and the intermediate volatility organic carbons, which sit somewhere in between. I'm also going to make a lot of reference to the oxidation flow reactor, the OFR. This is an equipment that is used to simulate atmospheric processes, and so it causes we force those VOCs in the OFR to form secondary organic aerosol. And a final bit of background. Why is secondary organic aerosol an issue? Well, secondary organic aerosol undergoes chemical transformation within the atmosphere and forms a component of PM2.5. PM2.5, particulate matter less than 2.5 microns. Why is that important? Well, because it can cause respiratory problems, heart disease. These particles can make their way into the lungs, and then they can't get out. They can't get out again. I just want to draw your attention to the fact that there are different sources of secondary organic aerosol, different sources of VOCs, and they fall into two classes really. The biogenic sources, which is anything natural. This comes from forests, it comes from trees, it comes from sea spray and from dust. Those biological processes, those natural sources can release materials into the atmosphere, form VOCs, and those VOCs can then form secondary organic aerosol and PM2.5. But also we have the so-called anthropogenic sources. These are the man-made sources, combustion, transport, burning of fuels, those sorts of things. But also bear in mind what I said before about those volatile consumer products. They have a significant influence. So the VOCs come together in the atmosphere. They're exposed to sunlight, ultraviolet radiation, and also oxidants, which are present in the air. And here we're talking about hydroxyl, ozone, nitrous oxides, sulfurous oxides. Under those conditions, they can then form the secondary organic aerosol, then we led, then into the PM2.5, and that then gets us into potentially into the lung and causing those respiratory problems, heart problems that we're hearing a lot about these days. So what did we do? And some of you will know this already, but in 2020, immediately after the publication of that first Yale paper, the industry formed the CARE group, the Coalition for Asphalt Research into Emissions. And it was a multi-party group involving Eurobitume, the Asphalt Institute in the USA, IAPA, the European Asphalt Paving Association, NAPA in the States, that's the National Asphalt Paving Association, European Waterproofing Association, and the Asphalt Roofing Manufacturers Association in the USA as well. First thing we did was to do a really, really deep dive into that publication. We involved academic colleagues from Europe and the USA to really dive into those publications and see if there was anything that we could find from that may give us an answer to why these results were causing us such concern. And then we entered into a dialogue with Yale University. That dialogue, I'm afraid, proved to be quite short-lived. We couldn't get to a consensus. And then we, with our good friends at Heritage Research in the USA, we attempted to replicate the research. And it turns out that we couldn't replicate the research. The findings were completely different. For our members, we then produced a Q&A document in case they were asked about this publication from Yale. And I have to say that the publication from Yale caused significant media interest, both in the scientific media, the trade press, and the mainstream press. This was everywhere. So it then became apparent to us that we needed to have a more accurate defense against the Yale work. And that it became very obvious then that we would need to commission our own research. And so in 2022, we started between the CARE group partners, we started to scope out what we felt we needed to do. And then made contact with a number of academic institutions. Towards the end of 2023, we had a preliminary meeting with the University of California at Riverside. I should have said that's what UCR stands for. It's the University of California at Riverside. We were impressed with the facilities that they had. In 2024, we signed a memorandum of understanding, and then we started the project. Who's involved in this study? It's Eurobitume, it's the Asphalt Institute, and it's NAPA, working alongside the University of California at its Riverside campus under the direction of Professor David Cocker, who is a renowned emissions and atmospheric chemistry specialist. In his time, he's published around about 180 papers. So we really couldn't have got a better institution and a better academic professional to lead the project. Within our organizations, we have contributed financially to that project, to this project, sorry. Eurobitume has contributed 100,000 euros, Napa $125,000, and the Asphalt Institute up to $250,000. So let's set the scene. Well, the first thing we have to do for this research was to prepare the samples, and we wanted to be absolutely certain that there was no room for doubt. We selected 3 PG 64-22 binders, the most common origins in use in the USA. They were Canadian, Gulf Coast and East Coast crudes, and we made absolutely certain that they were prepared blind. So there was no labeling other than A, B, or C in the samples going to University of California, Riverside. Why? Because we didn't want to introduce any bias, conscious or otherwise. We selected a Superpave 9.5 surface mix and compacted that to 6% air voids. When the samples were prepared, they were wrapped in PTFE film, sealed in polyethylene bags, and then shipped overnight. So from compaction to shipping to arrival in to the University of California at Riverside in just over 24 hours. So that's really quite impressive. Why did we do that? We wanted to make absolutely certain that the samples arrived at UCR in the best possible state. They were the youngest possible samples that we could ever achieve. So let's show you what happened. So here are our cores prepared. I just want to draw your attention to how clean that asphalt preparation lab is at UCR. At HRG. It was done in almost clean room conditions. Access to the preparation area was severely restricted. We even restricted the use of things like cosmetics and deodorants to make sure there was nothing that could possibly compromise the samples. We didn't introduce any materials that could have interfered with the results. The samples are bagged. That's the Teflon film being prepared into a polyethylene bag. Labeling, so just A, B, or C, into a refrigerator, then into a container, packed in dry ice to make sure that any volatile material is trapped, and then shipped over to UCR overnight. So that's the lab samples. Now let's have a look at our asphalt control samples. We also wanted to take samples from the field because there's been research published that suggests emissions from old asphalt samples is actually higher than from fresh asphalt samples, and we wanted to know why, and we wanted to confirm if that was real. Again, everything possible was done to make sure that the samples extracted from the field were as clean and as robust as they could be. You can see there the core being taken. Why do we want field age samples? Well, we wanted something that was going to compare with our lab prepared samples, and for that, we wanted a PG 6422 of known composition. So we needed to know where the bitumen had come from, what the asphalt composition was, and whether or not any surface treatments had been applied. And we were very, very fortunate to be able to secure a site of fully known core composition, which was 30 years old. So this was our asphalt in service. We also took out a sample of concrete. Why did we do that? We wanted to use that as a control, because if concrete is found to emit after 30 years, then there's a logical conclusion that the emissions from the concrete must be coming from things like tire rubber deposition, engine oil leakage, atmospheric deposition as well. So that's why we took our core. In terms of our project tasks, we decided on two distinct areas. The first is what we've called field emissions. Here we take our lab field and control samples, and we expose them to the atmosphere outside. So they're subject to fluctuations in temperature, fluctuations in light, and in that process, what we did was carry out two things: chemical speciation of the emissions. We wanted to know what chemical species were coming from the samples, and also the rate of emission. And we corrected for any background atmospheric issues. It was important that we did that because during the very early stages of the assessment, there was a wildfire in Canada and significant amounts of smoke and smog were released into the atmosphere. So we made absolutely certain that we corrected for that background. Our second task was the secondary organic aerosol formation. For that, we used just our lab prepared samples. We brought them indoors, a controlled environment. It was isothermal. We held the cores at 60 degrees for 21 days, and we measured the emissions from there, both in terms of mass and in terms of secondary organic aerosol. We chose 60 degrees because that was the reference temperature used by Yale in their original study, and their assumption was the pavement will stay at 60 degrees throughout its lifetime. We also varied thickness and surface area variation because we wanted to dive deeper into this statement made by Yale that it didn't matter where you were in the pavement, the emission pathway was unaffected. It didn't matter if you were 20 millimeters below the surface or 40 millimeters below the surface, those volatile organic carbon species could come out. And we took those emissions from the lab cores into our OFR and also into an environmental simulation chamber. Let's just show you the task one setup. This is on the roof of UCR. We had to move the samples up onto the roof because there was an issue with, shall we say, visitors to the campus site. So while it would be great to have those samples down at ground level, it was simply too risky to do it at ground level. So we did it at roof level, but the temperature and airflow around the roof at the UCR building was practically identical to that at ground level. So there was no issues in variation of temperature and airflow. We took our cores, we encased them in a specialist Teflon bag with an input manifold and an output manifold, where we push ultra pure air through the sample and we measure what's coming out of it. You can see the samples being placed here. And once we've got everything done, we have this big manifold. Let's see if I can use my laser pointer. You have all of the samples here and here. We have an inlet manifold of ultra pure air, and then it circulates down into the detection equipment at UCR. So that's our exterior setup. What's the status? We have completed the testing, and we've had a first draft report, which I mentioned to those of you that were present in Prague. This morning, we have actually received a second draft report, which the three partners will be looking at extensively over the next couple of days, and a peer-reviewed publication is under development. So it's been a very, very good piece of work. Appreciate that was a long introduction. You're all here to find out what does it mean. But I think it was important that you had that introduction. So let me take you back to what Yale said. 0.1% mass loss over the lifetime of the asphalt, and the emission path was unaffected by the location in the asphalt. In our deep dive of that publication, we were searching for the sample. What was the sample? Because it wasn't immediately clear what had been done. After the deep dive and looking at the supplementary data and previous publications, it became evident that what had been used was a 12-gram sample of fresh asphalt, heated at 60 degrees. And if you can try and visualize that, it's about 10 millimeters by 1 by 1. It's around about that sort of size. So what's our UCR study told us? Well, in simplistic terms, the emissions do increase with temperature. We should expect that. The emissions also increase with ultraviolet light. I'm not an atmospheric specialist, but again, you would expect that. And the main species that is emitted is carbon-15 alkane, decapentane, or pentadecane, sorry. All three of those samples are absolutely consistent with the publication from Yale. What else have we found is that our thicker samples seem to retain emissions to a certain extent. And the thicker the sample, you get slightly more prolonged emissions over time. I'm going to qualify that when we go through to the absolute findings. Emissions are strongly dependent on surface area, much less so than on sample thickness, and our secondary organic aerosol formation is extremely low, and it needs to be forced. So secondary organic aerosol formation does not happen automatically. It needs to be forced, and I'll come into the reasons behind that in a moment. But keep in mind, the formation is extremely low. Just to give you more detail before we come to the results of the outdoor studies, these are the task 1 studies. You can see the manifold there. In addition to our lab samples, we had our 17-year-old asphalt and concrete. The measurements took a month. We've done our chemical speciation. We've looked at VOC, IVOC, SVOC release. And out of it, we got C15 alkane. which we measured at somewhere between 0.2 micrograms per cubic meter and 0.02 micrograms per cubic meter, which is 10 to 100 times lower than Yale. Just to help you visualize, because it's not necessarily clear from that picture of the manifold and the samples. So what we did was we pumped ultra clean air into the core. Air species comes out of it, absorbed on two separate absorbent tubes. First, a TDS, a thermal desorption tube, which is specific for our VOC collection, and second into an XAD2 tube, which is a resin absorption medium for the other species. So, what did we get out of that? Well, you can see from the graph, I appreciate it's quite difficult. There's a lot of data on there. But our main components are the ones highlighted. I couldn't put a full legend on this because it would make it practically unreadable. So I've just highlighted the C12, C13, C14, C15, and C16 species because those are the main components. Along the bottom is our axis in days, and what I want to draw your attention to is what happens after day 9. So you can see day 18, day 25, the concentration of those species, and it's in micrograms per cubic meter, has dropped to practically 0. So real-time emissions are dropping to practically 0 in the real world environment after 18 to 25 days. That's quite a significant finding. Moving on to our indoor studies, it's a similar experimental setup. This time the cores are encased in polystyrene foam, still inside their Teflon bags, and they're subjected to heat and UV. Aim is to get this to be completely isothermal, 60 degrees, and measure secondary organic aerosol formation. For this, we chose our Canadian bitumen PG64-22, held it at 60 degrees for up to 21 days. We varied the thickness of 150 millimeter core from 115 down to 38. Did all those studies in triplicate. We varied our surface area as well, from 150 to 100. Now you might ask, why when we moved to a 100 millimeter core, why did we make it thicker? That was to make sure that the mass of asphalt, mass of bitumen was identical. Again, that was done in triplicate. Then we passed all of the emissions either into our oxidation flow reactor or into the environmental chamber. This is what it looks like. I'll just use my laser pen again. So this is the sample itself. We're pumping ultra pure air into our asphalt or over our asphalt. We've got a heating lamp. It moves into our oxidation flow reactor. Again, we inject ozone and humidity into that. It passes through the OFR, and we pass it into what's called an SMPS, a scanning mobility particle sizer, and that measures our PM 2.5 or others. We need ozone to generate that secondary organic aerosol. If you remember that slide I showed early on about how secondary organic aerosol and PM 2.5 form, you need something there to generate them. So what do we find? Well, here's the impact of temperature on emissions. Two different curves here. The orange curve, this is the temperature of the core increasing, and the blue trace is our concentration of emissions. And then you can see that the emissions do increase as temperature increases. But I also want to draw your attention that it's not consistent, that it increases and then decreases, increases, decreases. Once we get to that steady state of around of 60 degrees, we're still finding an increase in emissions followed by a sharp drop, increase in emissions followed by a sharp drop. It's almost as though the asphalt sample is breathing. So there are materials being ejected, and then it relaxes, and it ejected, and then it relaxes. A significant finding, that, because again, it calls into question the presumption of unabated release of emissions suggested by Yale. When we do this over a longer time, so we've got the emissions here being measured, excuse me, being measured over a full day. We check the background air. There's nothing there. There's no rogue material coming through. And then we start to heat our core up to 60 degrees. And you can see this breathing again. Increase in emissions, drop in emissions, increase, drop. And then it starts to settle down. And then as we cool it down, the emissions drop to zero. Also want to draw your attention to this mass concentration scale here. Note that the maximum that we're getting is about 8 micrograms per cubic meter, and then it drops away pretty rapidly. What happens when we look at our different depths of cores? So, two things to bear in mind with looking at this graph. First of all, and the most important thing, is there is a decay. There is a decay in emissions over time. Vitally important in our defense against the Yale paper. Secondly, the deeper cores, the decay is not as rapid as it is in the thinner cores. Thirdly, the concentration scale on the y-axis, and the horizontal line, which you can see at 10 to the minus 1 micrograms per cubic meter. Just to put this into perspective, and I know I'm talking to a technical audience here, a grain of sand weighs about 1 milligram. Our detection limit is 0.1 of a microgram. So that's 1/1000th of a grain of sand. I just think it helps to put these things into perspective. By the time we get to day 7, thinner core.
Excuse me, Ian. Time is exactly my keyword. Thank you.
Okay. By day 7, the emissions have dropped below the detection limit for all samples. Very, very significant. In terms of thickness, what can we conclude? Well, after 14 days, the emissions decay below the detection threshold. That's very important. Thicker cores do have slightly higher emissions, but they also decay. Everything decays within over time. And we need to remember that when we're talking about surface area effects, we're not just talking about the absolute surface, because if we have interconnectivity of voids, obviously we have a bigger surface area. To look at ultraviolet exposure, exactly as predicted, the ultraviolet light, which is the blue trace, enhances the formation of secondary organic aerosol precursors by 2 to 5 times. But keep an eye on that scale. Keep an eye on that that y-axis, which is peaks out at 3.5 micrograms per cubic meter. Onto the environmental chamber studies. This is one of the reasons we wanted to be at Yale. Sorry, not Yale, UCR. My bad. UCR have got 3 environmental chambers, including the biggest one in the world, which is 120 cubic meters. They also have a 37 cubic meter one and a 28 meter cubed one. These chambers are used to look at emission studies, wood smoke, emissions from agriculture, etc. For this study, we used the 37 cubic meter atmospheric chamber. We did a similar thing. We had our ultra clean air going into over the asphalt, heating lamp, UV lamp, into the environmental chamber study, into the environmental chamber where we inject 100 part per billion NOx, and then eventually 1 part per million of hydrogen peroxide. Here's the result from the environmental chamber study. We get nothing other than a couple of very tiny spikes. No SOA formation, even after the injection of nitrous oxide. We carry on the study, and then we inject a significant quantity of hydrogen peroxide, and then and only then do we get to see secondary organic aerosol formation, but the concentration is extremely low. Now we'll come to a couple of perspectives. What do the results actually mean? Well, if we look at our mass loss, we measure mass loss of just under 6,000 micrograms from a core which weighs about 4 3/4 kilograms. And if we assume the mass loss has a 10% conversion to secondary organic aerosol, that's pretty reasonable to assume that. We get a mass loss of, we get 592 micrograms of secondary organic aerosol. We can convert that to a percentage from the total core, and it gives us a figure of 0.000124%. Now remember that Yale said it was 0.1%. So we're 3 orders of magnitude lower. Let's look at perspectives. If we assume all the binder is available in a core and it emits at a steady state over 20 years, and we do that sort of calculation that we've just done, we will get to a total mass loss of 0.00257. And that's 40 times lower than Yale predicted. But that's assuming that emission is at a steady state throughout the lifetime, and we know that it isn't. So if we factor in our exponential decay, the mass loss over 20 years is even lower. It's 0.0015%, and that's 700 times lower than Yale. If we can then turn these calculations into a prediction of what would happen in LA County. Why is it LA County? Because that's where the Yale study was originally referenced. Total asphalt emissions we can calculate at about 16 kilograms of asphalt per day. Emissions from all the asphalt in LA County. The air quality management plan for California estimates that there's, from all sources, 81,000 kilograms per day. So the asphalt contribution, if you just look at total emissions, is 0.019%. I would argue that is not significant. However, If we then convert that to a secondary organic aerosol formation, then the contribution is 0.003%. Again, I would argue that is not significant. We are coming to the end. I know there has been a lot to take in, but to summarize, the UCR study indicates significantly lower emissions than Yale. And we're talking worst case scenario, 2 to 4 orders of magnitude lower. The emissions decay rapidly. After 14 days, they're below the detection threshold of the instrumentation. And we use the most sophisticated instrumentation for this. The emissions are surface or at worst near surface related. Nothing coming from deeper in the pavement. We have our second draft report, and the paper has been submitted to Environmental Science and Technology. It was submitted last week, and we are awaiting feedback on that. I have to say, this has been one of the most exciting projects I've been involved with within Eurobitume. And it has been a pleasure working with Dr. Cocker, Paul Soey from the Asphalt Institute, Howard Marks from NAPA, and Jim Mertes from NAPA. It's been a very well organized project, and it's been extremely valuable to us as Eurobitume, but also to the industry. I'm going to thank you. If you need more information on this, obviously you can talk to me. I haven't been able to see anything that's going on in the chat. These are our contact details. I'm now going to hand back to Anya and say thank you for your attention.